Hello students, I hope you all are doing good. So today we will solve NCERT exercise of chapter Wave Optics. So this is our disclaimer. So by the end of this lecture, you will have a strong understanding of fundamental concepts such as wavelength, frequency and speed of light in various media, and we will solve some questions on how wave propagate through different optical elements. Okay, we will see how wavelength, frequency and the speed of the light are interconnected. For example, the speed of light changes when it moves from air to water, affecting how we perceive objects underwater. After, we will apply these principles to Young's double slit experiment, a classic demonstration of interference. This experiment helps us solve problems involving fringe patterns, path difference and intensity variations. Okay, so you will be able to apply these principles and you will be able to understand the fundamental concept, and you will also understand the application of these concepts. So there are total of 6 NCERT exercise questions in chapter Wave Optics. Okay, and in today's lecture we will be covering all the exercise questions from 10.1 to 10.6. As we go through each question, pay attention to how they build the concepts we have discussed in class. Okay, so our first question, the problem asks us to determine the wavelength, frequency and speed of both reflected and refracted light when monochromatic light of wavelength 589 nanometer is incident from air onto water. Okay, the refractive index of water is given 1.33, which is crucial for solving the problem. Firstly, student, think about we solve this problem from the given data. So we'll be looking at how the properties of light change when it reflects and refracts. The question asks for wavelength, frequency and speed of both reflected and refracted light. So let's start by the given information. We know the wavelength of the monochromatic light in air is 589 nanometer, which we convert to meters as 589 into 10 to the power minus 9 meter. Okay, so we are converting it into SI unit meter. Now refractive index of the medium is given, which is n equal to, what is the medium here? Water. So refractive index of medium, or we can say water, is given n equal to 1.33, and refractive index of air, which is n air, is given, what is the refractive index of air? 1. So let's begin by examining the reflected light. When light reflects off a surface, it stays in the same medium. Okay, so let's focus on calculating the wavelength of the reflected light. So notice how wavelength, frequency and speed of light remains unchanged upon reflection. This is because the light is still traveling through air, the same medium it was in before hitting the surface. Okay, so it is in air and hitting the surface of water, it is reflected back in the same medium. So if it is reflected back in the same medium, so its wavelength will remain same, also its frequency and speed will remain same after reflection. Okay, so what does this mean for the wavelength of reflected light? It means that it will be same as the incident light. So we see the wavelength of reflected light explicitly stated as 589 nanometer. Okay, so it will be equal to wavelength of incident light. So wavelength of reflected light is also 589 nanometer, just like the incident light. So now calculating the speed of light in different media. This is crucial because the speed of light changes depending on the medium it travels through. Okay, speed of the wave in a medium is determined by refractive index. Okay, and the formula we will use is V equal to C upon N. Okay, so the formula is V equal to C upon N according to NCERT equation 10.4. The equation tells us that the speed of light in a medium is inversely proportional to refractive index. So as the refractive index increases, the speed of light decreases. So let's apply this formula to air. Since the refractive index of air is approximately 1, the speed of light in air remains the same as in the vacuum. Okay, so using the formula, we find that the speed of reflected light in air is simply c. The speed of light in a vacuum, okay, so c is speed of light in vacuum, because refractive index in air is 1. Reflected light is also in air, so velocity of reflected light will be c upon n air. So n air is 1. So reflected light, speed of reflected light is equal to c. And what is c? Speed of light in vacuum. Okay, so that means the speed doesn't change when light reflects off the surface. So to emphasize, the speed of the reflected light is 3 into 10 to the power 8 meter per second. This is a constant value for light traveling through air or reflecting off a surface back into air. So the speed of reflected light remains unchanged at 3 into 10 to the power 8 meter per second. This is because the refractive index of air is 1, so the speed of light is not altered. So now calculating the frequency of light. Frequency is a fundamental property of waves that tells us how many waves cycles pass a point per second. It's important because it remains constant when light moves between different media. So relationship between wavelength, frequency and speed of an electromagnetic wave in a medium. Okay, so this is given by equation. This relation is given by the equation frequency equal to speed upon wavelength. Okay, so the formula we are using is frequency nu is equal to speed v upon wavelength lambda. So this tells that frequency is directly proportional to the speed and inversely proportional to the wavelength. Okay, as speed increases, frequency. Okay, so this is the relation. So for the reflected light, the medium is air. So speed of light is the speed of light in a vacuum. Okay, speed of v is equal to, for reflected light, speed of reflected light is equal to the speed of light in the vacuum or air. Okay, as denoted by c. And the wavelength remains same because reflected light is in same medium. After reflection, it goes in same medium. So wavelength remains 589 nanometer. This means the frequency of the reflected light will be calculated using these values. So now let's calculate the frequency of the reflected light. So using the formula, frequency is equal to speed of light in air, that is c, upon wavelength of reflected light, that is lambda reflected. So we can find the frequency from here. So formula for frequency, speed of light upon wavelength of reflected light. So after putting the value, substituting the values into the formula, frequency is equal to 3 into 10 to the power 8, that is the value of c, divided by 589 into 10 to the power minus 9 meter, that is the wavelength of reflected light. So this step is crucial for ensuring our calculation are accurate. So after doing the calculation, we find that frequency of reflected light is approximately 5.09 into 10 to the power 14 hertz. This result shows us how high the frequency is for visible light, which is why it can be detected by our eyes. So the frequency of reflected light remains approximately 5.09 into 10 to the power 14 hertz. Now let's dive into the part B of our problem, which involves the refracted light. This is the light that passes through the water surface. Okay. So calculating the speed of the refracted light in different medium, that is water here. So speed of the wave in a medium, that is water, is determined by the medium's refractive index. The formula we will use is speed of refracted light equals to speed of light in vacuum divided by the refractive index. So V refracted is velocity of refracted light is equal to c upon n. C is the speed of light in vacuum and n is the refractive index of the medium, according to NCERT equation 10.4. So let's substitute the values we have into the formula. We know C is 3 into 10 to the power 8 meter per second, and refractive index N for water is given 1.33. Okay, so by performing the calculation, we find that speed of refracted light is 3 into 10 to the power 8 divided by 1.33. This step is crucial for understanding how much slower light travels in water compared to air. So after calculating, we find that speed of the refracted light is approximately 2.26 into 10 to the power 8 meter per second. So hence the speed of the refracted light will be 2.26 into 10 to the power 8 meter per second. So calculating the frequency, it's crucial to understand that when light travels from one medium to another, its frequency remains unchanged. This means the frequency of the refracted light is the same as the incident and reflected light. So here we see the equation nu refracted equal to nu incident equal to nu reflected. So frequency will remain same. Okay, so if the light is reflecting or refracting, frequency will not change. Okay, so frequency is the identity of any wave. So this equation highlights that the frequency remains constant across the different media. So the frequency of the refracted light is equal to 5.09 to 10 to the power 14 hertz that we have calculated earlier for reflected wave. Okay, and frequency of refracted light is 5.09 to 10 to the power 14 hertz again. Okay, this reinforces the idea that frequency remains unchanged during the refraction. So the relationship between wavelength, frequency, and speed of electromagnetic waves in medium. This is a fundamental concept in wave optics. So the equation we use to describe this relationship is lambda equal to V upon nu, where lambda is the wavelength, V is the speed of light in medium, and nu is the frequency. So we have the frequency nu refracted equal to 5.09 to 10 to the power 14 hertz, and the speed V refracted as 2.26 into 10 to the power 8 meter per second. Okay, so substitute these value in the above formula. So using the formula, we substitute the values to find lambda refracted. So lambda refracted is equal to V refracted upon nu refracted. So which is 2.26 into 10 to the power 8 upon 5.09 into 10 to the power 14. So after solving the calculation, we find that lambda refracted is approximately 450 into 10 to the power minus 9 meters or 450 nanometer. This result shows how the wavelength of light changes when it enters a medium with a different refractive index. So the wavelength decreases due to higher refractive index of water. Okay, so on the refracted light, we need to calculate its wavelength in water using the formula for wavelength in a medium. Lambda refracted is lambda air upon refractive index. We can write this formula also. Okay. So lambda refracted is approximately equal to 450 nanometers. So hence the wavelength of refracted light will be 450 nanometers. So next question, exercise 10.2. So question is asking about the shape of wavelength in cases given below. Light diverging, first case is light diverging from point source. Second case is light emerging out of a convex lens when a point source is placed at its focus. Okay, and third C part is the portion of the wavefront of light from a distant star intercepted by the earth. So let's see. So let's examine the first case, light diverging from a point source. Notice how the wavefronts are spherical. This is because the light spreads out uniformly in all directions from the point source, forming concentric spheres. Okay, picture throwing a stone into a pond and watching the ripples spread out in circles. Okay, so why the shape is spherical? Because locus of all points vibrating in same phase. Okay, so the particles that are equidistant from the point source are vibrating in same phase. Okay, so that locus of that points will be forming sphere. Okay, so wavefront will be of the shape of sphere in the case of point source. So let's examine what happens when light emerges from a convex lens with the point source at its focus. In this case, the wavefront becomes a parallel grid. Okay, also known as a plane wavefront. This transformation occurs because the lens bends the light rays to travel parallel to each other. Okay, notice how the wavefront changes from spherical to planar, illustrating the lens focus effect. Okay, so wavefront is spherical initially, and point source is placed at the focus of the convex lens. So rays that are emerging from the point source becomes parallel after refracting through the lens. Okay, so initially wavefront at any point is perpendicular to the direction of light propagation. Okay, so after refraction, rays are parallel to principal axis. So wavefront will be perpendicular at any point to the rays. So rays are parallel, so wavefront is perpendicular grid. Okay, so which is known as plane wavefront. Okay, or sorry, we can say parallel grid. So parallel to the lens. Okay, or it is known as plane wavefront, which is perpendicular to the direction of propagation of light. Got it? So this is the plane wavefront that is emerged after refraction through the convex lens when point source is placed at the focus. So now let's focus on the light from a distant star. Because star is so far away, the light waves that reach Earth can be considered parallel. So wavefront can be considered plane. Okay, either star is a point source. When viewed from Earth, star is a point source. So for point source, shape of wavefront is spherical. But star is very large distance from the Earth. Okay, due to which the spherical wavefront that is reaching our Earth is very large. The radius of this sphere is very large. So the portion, or we can say wavefront of the light from a distant star that is intercepted by the Earth, okay, that is noticed at the Earth, is plane wavefront. Okay, in the diagram you can see that if a point source is a distant source, okay, so how spherical wavefronts are there, but a small portion of the spherical wavefront will be plane. Similarly, star is very far from the Earth, so spherical wavefront that is reaching our Earth is very large, and radius of curvature of this spherical wavefront is huge. Okay, so it is looking like, so it is less curved and it is looking like plane wavefront. So this is similar to how we perceive sunlight as parallel rays. We perceive sunlight as parallel rays and not diverging rays. Okay, so for parallel rays, wavefront is plane. Okay, so notice the diagram illustrating this concept where a small portion of spherical wavefront is approximated as plane wavefront. This simplification helps us understand how light behaves over vast distances. Okay, now next question. So refractive index of glass is 1.5. What is the speed of light in glass? Okay, and speed of light in vacuum is 3 × 10⁸ meter per second. This problem tests our understanding to how to apply the concept of refractive index to calculate the speed of light in medium. So the second part of the question asks whether the speed of light in glass is independent of the color of light. Okay, or this explores the concept of dispersion, where different colors of light travel at different speeds in a medium due to varying refractive indices. Okay, so is the speed B part is the speed of light in glass independent of color of light, or if not, which of the two colors, red and violet, travel slower in a glass prism? So let's see the solution. So let's dive in the solution. First, we will list the given information. So we specify the refractive index of glass, which is 1.5. Okay, so this value tells us how much the speed of light is reduced when it enters the glass compared to its speed in a vacuum. Next, we have the speed of light in vacuum, which is 3 into 10 to the power 8 meter per second. Now let's look at the formula that relates the speed of light in a medium to its speed in a vacuum and refractive index. So formula we use is V equal to C upon N according to NCERT equation 10.4, where V is the speed of light in medium, C is the speed of light in vacuum, and N is the refractive index of the medium. So by substituting the given values into the formula, we calculate the speed of light in glass. We divide 3 times 10 to the power 8 upon 1.5 to find the result. Okay, so calculation gives the speed 2 multiplied by 10 to the power 8 meter per second for light traveling through the glass. This is significantly slower than its speed in a vacuum, illustrating the effect of refractive index. So hence the speed of light in the glass will be 2 into 10 to the power 8 meter per second. So now let's consider how the speed of light in the medium is affected by the color of light. The speed is not constant for all colors. This is an important concept because it helps us understand phenomena like dispersion, where different colors of light spread out. So shorter wavelengths like violet travel more slowly through a medium. This happens because they experience greater interactions with the medium's atom. Think of it like crowded room where smaller people have a harder time moving through the crowd. So this increased interaction results in a higher refractive indices for shorter wavelengths. Consequently, colors with shorter wavelengths like violet will travel slower compared to the colors with longer wavelength like red. This is why violet light bends more than red light in a prism. Okay, so let's focus on the wavelengths of red and violet color. Red has a longer wavelength compared to violet light. The difference in wavelength is crucial because it determines how each color interacts with the medium. So finally, we conclude that violet light travels slower than red light in the glass. This is due to its shorter wavelength and greater interaction with the medium. Next question. So this question from Young's double slit experiment. The question provides key measurements. The slit separation is 0.8 millimeter. The distance of the screen from the slit is 1.4 meter, and the distance between the central and fourth bright fringe is 1.2 centimeter. That is x4 is given for bright fringe. This problem tests your understanding for the interference pattern created by the coherent light sources and how to apply the formula for fringe spacing in double slit experiment. And what is asked? So you have to determine the wavelength of light used in the experiment. So let's begin by listing the given information. So first we have the distance between the slits, that is given d equal to 0.2 millimeter, which we convert to meters for consistency over calculation. So it will become 0.28 into 10 to the power minus 3 meter. So next we have the distance from the slits to the screen labeled d. This is 1.4 meters. This distance is important because it affects the spacing of the interference fringes on the screen. We also know the distance between the central bright fringe and the fourth bright fringe, which is 1.2 centimeter. We convert this to as meters as well. This measurement will help us find the wavelength of the light used. So in Young's double-slit experiment, the position of nth bright fringe from the center is given by the specific formula. This formula relates the fringe position to the wavelength of light, the distance between the slits, and the distance to the screen. So the formula is xn equal to n lambda d upon small d, according to NCERT equation 10.13. Okay, where n equal to 0, plus minus 1, plus minus 2, and so on. And lambda is the wavelength of light used. So let's start by looking at the formula for the position of nth bright fringe, xn equal to n lambda d upon d. Okay, again. Now we arrange this formula to solve for wavelength lambda equal to xn small d upon n capital D. Wavelength is directly proportional to the distance between the fringes and the slit separation. So let's substitute the given values into our formula. We have n equal to 4. Okay, we know the position of fourth bright fringe. So n equal to 4, d equal to 0.28 into 10 to the power minus 3 meters. Capital D is 1.4 meters and x4 is given. Position of fourth fringe 1.2 into 10 to the power minus 2 meter. By putting these values into our equation, we can find the wavelength of light used in the experiment. So substituting these values, we get lambda equal to 1.2 into 10 to the power minus 2 multiplied by 0.28 into 10 to the power minus 3 upon 4 into 1.4. So after performing the calculations, we find that the wavelength lambda is 6 into 10 to the power minus 7 meters. This result is typically for visible light, which confirms that our calculations are consistent with the expected range for light wavelengths. Okay, so lambda equals to 6 times 10 to the power minus 7, or we can write it as, convert it into more familiar unit. The wavelength we can calculated 6 into 10 to the power minus 7 meters, and we convert it into 600 into 10 to the power minus 9 meter, and 10 to the power minus 9 meter is nanometer. So wavelength is 600 nanometer, which lies in the visible region. So next question. So this question is also about Young's double slit experiment. Question provides a specific scenario. The intensity at a point where the path difference is equal to wavelength lambda is given as k units. The problem asks to determine the intensity at a different point where the path difference is lambda by 3. Okay, this question tests our understanding of the relationship between the path difference and light intensity in interference pattern. Okay, so wavelength lambda is given and intensity of light at a point, resultant intensity of a light at a point on the screen where path difference is lambda is k, and we have to find the intensity of light at a point where path difference will be lambda by 3. So let's start by noting the given information. We have monochromatic light with the wavelength denoted by lambda. In Young's double slit experiment, intensity of light at any point on the screen is determined by a specific formula. This formula allows us to calculate the resultant intensity based on the interference of light waves. So the formula for the resultant intensity is I equal to 4 I naught cos square phi by 2. Here I is the intensity at a point on the screen, that is resultant intensity. I naught is the intensity of light from the source, and phi is the phase difference. Okay, so phi is the phase difference between two waves reaching at point on screen, and I naught is the intensity of light from the source being used. Let's start by considering the case where the resultant intensity is k units and the path difference between the waves is exactly one wavelength lambda. To find the resultant intensity at different path differences, we need to determine the phase difference between the waves. This phase difference is crucial because it directly affects how the waves interfere with each other. The relationship between the phase difference phi and path difference delta p is given by the specific formula. This formula helps us calculate the phase difference based on the path difference. So the formula we use is phi equal to 2 pi upon lambda multiplied by delta p. Here phi represents the phase difference, lambda is the wavelength, and delta p represents the path difference. So let's apply this formula to our specific case. When path difference is equal to lambda, we can calculate the phase difference phi 1. So substituting the path difference of lambda into the formula, we find that phi 1 equals to 2 pi upon lambda multiplied by lambda. Okay, so which result in 2 pi. This means the waves are in phase. Okay, leading to the constructive interference and maximum intensity. So now let's start solving the problem. We know that the path difference is lambda, phase difference we have calculated phi 1 equal to 2 pi, and the intensity I1 is equal to K for first case. Okay, so we use the formula for resultant intensity, I equal to 4I0 cos square phi by 2, and putting this value I1 equal to 4I0 cos square phi 1 upon 2. Now substitute this value, substitute the known values into the formula. We have, so I1 is K, so K is equal to 4I0 cos square, what is phi 1? 2 pi upon 2. So after solving, what is cos 2 pi upon 2? So it will become pi. So what is cos pi? It is minus 1, and cos square pi, so minus 1 square is 1, so cos square pi is 1. Okay, so K will result in 4I0, where cos square 2 pi is, cos square pi is 1. This simplification shows us that intensity K is directly related to the initial intensity I0. So equation K equal to 4I0, we can solve for I0, giving I0 equals to K upon 4. This tells us that the base intensity or initial intensity of the source of the light source used in experiment, which is a quarter of the intensity K at the path difference of lambda. So now we conclude the intensity of light being used is the experiment is K by 4. Okay, so let's start by considering a specific case where the path difference between the waves at a specific point on the screen is lambda by 3. Now we will determine the phase difference at this point. We will call it phi 2. The phase difference is a measure of how out of step the waves are with each other. So we calculate the phi 2 using the formula phi 2 equal to 2 pi upon lambda multiplied by the path difference. That is here lambda upon 3. So this equation helps us convert the path difference into a phase difference. So after simplifying, we find phi 2 equals to 2 pi upon 3. So what is 2 pi upon 3 angle? It is 120 degree. Okay, so this tells us the waves are 120 degree out of phase at this point. So this is not entirely constructive interference, not entirely destructive interference. Okay, so now let's continue with the solution. We start by substituting the given values into our intensity formula. Here phi 2 is 120 degree. Okay, and I0 is K by 4. So now put it in the formula for resultant intensity. So I2 equal to 4I0 cos square phi 2 upon 2. So put these values. So I0 will be equal to, what is I0? K by 4. So 4 into K by 4 cos square, what is phi 2? It is 120 degree. So 120 degree upon 2. So let's simplify the equation. We find that I2 equals to K times 1/2 squared, because cos 60 degrees 1 by 2. So cos square 120 degree upon 2 will become cos square 60 degree. So 1 by 2 square. Okay, and K by 4 multiplied by 4 will become K. Remember, cosine of 60 degrees 1/2. So after simplifying, we find that I2 equals to K divided by 4. This result shows that intensity at point where the path difference is lambda over 3 is also K by 4. Okay, so intensity of light at the point where the path difference is lambda over 3 is k divided by 4 units. Now, coming to our last question, there are two parts in the question. Part A of the question asks us to find the distance of the third bright fringe from the central maximum for a wavelength of 650 nanometer. Okay, so this problem tests your understanding of how to calculate fringe position using the interference formula. Part B asks for the least distance from the central maximum where bright fringes due to both wavelengths coincide. This part tests our ability to find common positions for different wavelengths, which involves finding a common multiple of wavelengths. Okay, so there are two lights of wavelength 650 Newton and 520 nanometer and 520 nanometer. Okay, so they are used to obtain interference fringes in a Young's double slit experiment. So first part is you have to calculate the distance of third bright fringe from the central maxima. Okay, for first wavelength, that is 650 nanometer. And second part, which is very important from the competitive exams point of view. Okay, so you have to find the position from the central maximum where bright fringes least distance. You have to find from the central maximum where bright fringes due to both wavelengths coincide. So let's look at what we are given in the problem. We have a beam of light with two different wavelengths. Okay, so we have the first wavelength 650 nanometer. This is the longer wavelength of the two, and it will affect where the bright fringe appear on the screen. Now we have the second wavelength 520 nanometer. This shorter wavelength will create a different set of fringes. Comparing these two wavelengths will help us find where their bright fringes coincide. Next, let's define the distance from the slits to the screen, which we will call D, capital D. The greater the distance, the more spread out the fringes will be. We also need to consider the distance between the two slits, which we will denote as small d. So let's start with part A of our question. We need to find the distance of the third bright fringe from the central maximum for the wavelength of 650 nanometer. Okay, this will help us understand how different wavelengths affect the position of interference fringes. So in double slit experiment, position of nth bright fringe from the center is given by the formula xn equal to n lambda capital D upon small d according to NCERT equation 10.13. Okay, so where n equal to 0 plus minus 1 plus minus 2 and so on, and lambda is the wavelength of light used. So for the third bright fringe, n equals to 3 and lambda here is lambda 1, that is 650 nanometer. Okay, so by substituting, so for third bright fringe n equal to 3 and lambda 1 equal to 650 nanometer and xn is equal to n lambda capital D upon D. So put these values into this formula. Okay, for third bright fringe. Okay, so after substituting x3 will be equal to n becomes 3, lambda is 650. So 3 into 650 multiplied by capital D upon small d. So we are not given the distance of screen from the slits and separation of the slits. So we will write them as it is in the form of notations, capital D upon small d, nanometer. So again x3 equal to 3 multiplied by 650 capital D upon small d nanometer. So now let's simplify the calculation by multiplying. We get, so by multiplying 3 into 650, we get x3 equal to 1950 capital D upon small d nanometer. This gives us the distance of the third bright fringe from the central maximum for the 650 nanometer wavelength. So hence the third bright fringe for 650 nanometer wavelength is located at 1950 capital D upon small d nanometer from the central maximum. This shows us how the wavelength and fringe number affect the position of bright fringes in the interference pattern. So let's start by understanding the concept of fringe width in the Young's double slit experiment. The formula for fringe width is lambda multiplied by capital D upon small d, where lambda is the wavelength and capital D is distance to the screen and small d is the distance between the slits. So fringe width is directly proportional to the wavelength. This means that as the wavelength increases, the fringe width also increases. So if we have light with a longer wavelength, the fringes will be spaced further apart. So this relationship implies that fringe width for 650 nanometer wavelength will be wider compared to the 520 nanometer wavelength. This difference in fringe width is crucial for understanding how the interference pattern changes with different wavelengths. So let's start by understanding the position of bright fringes in Young's double slit experiment. The position of nth bright fringe from the center is given by the relation xn equal to n lambda capital D upon small d. This equation tells us how the position of bright fringe depends on the wavelength of light used. Okay, the position changes with the different values of n and lambda. Okay, where n equal to 0, plus minus 1, plus minus 2, and lambda is equal to wavelength of light used. So next consider, so due to lambda 1, wider bright fringes are formed, and due to lambda 2, thinner, less spaced fringes are formed as compared to the first wavelength. Okay, so greater number of fringes will be coinciding with the less number of fringes due to lambda 1. Okay, means if fourth bright fringe of lambda 1 is there, it will be coinciding with the bright fringe that is of higher order for lambda 2. Okay, so fringes of due to lambda 2 wavelength is thinner and fringes due to lambda 1 wavelength is wider. Okay, so if we consider that fourth bright fringe of due to wavelength lambda 1 is there, so it will be coinciding with bright fringe of higher order than 4 due to lambda 2. Okay, because fringes due to lambda 2 are thinner. Okay, so consider when bright fringes from different wavelengths coincide. We assume that nth bright fringe for one wavelength, that is lambda 1, coincides with the n plus 1th bright fringe for another wavelength, that is lambda 2. So higher order bright fringe will be coinciding with the bright fringe due to lambda 1. So higher order bright fringe due to lambda 2 is coinciding with the lower order bright fringe due to lambda 1. So to find the overlap, we equate the conditions for bright fringes xn for lambda 1 and xn plus 1 for lambda 2. This means the position of the nth bright fringe for one wavelength lambda 1 is same as the position of n plus 1th fringe for the other wavelength lambda 2. So using the equation n lambda 1 capital D upon small d is equal to n plus 1 lambda 2 capital D upon small d. So let's start by examining the condition for the bright fringes to coincide. Okay, again writing equation n lambda 1 capital D upon small d is equal to n plus 1 lambda 2 capital D upon small d. So after rearranging or simplifying the equation, n lambda 1 equal to n plus 1 lambda 2, this form is easier to work with the and shows the relationship between two wavelengths. Okay, capital D upon small d is cancelled from both sides. So let's substitute the given values for the wavelengths. We have lambda 1 as 650 nanometer and lambda 2 as 520 nanometer. This substitution will help us find the specific value of n where the fringes coincide. So substituting the values, we get n multiplied by 650 equal to n plus 1 multiplied by 520. This equation allows us to solve for n, the number of fringes for 650 nanometer wavelength where it coincides with the 520 nanometer wavelength. So after simplifying, rearranging the equation, we have n 650 minus 520. We have multiplied the above equation 520 in the bracket part, so it will become 520n plus 520. Okay, so we have brought the 520n in the left side, so it will become 650n minus 520n. So n will be taken common, so 650 minus 520 equal to 520. Okay, so n equal to 650 minus 520 equal to 520. So after simplifying the equation by dividing, and it will become n equal to 520 upon 130. And we found the value of n. So n will be equal to 4. So nth bright fringe of due to lambda 1 is coinciding with n plus 1th bright fringe of lambda 2. Means 4th bright fringe of lambda 1 is coinciding with 5th bright fringe of lambda 2. So this tells us that 4th order of 650 nanometer wavelength will coincide with the another order, that is 5th order of 520 nanometer wavelength. Okay, so we conclude that 4th maxima of 650 nanometer wavelength and the 5th maxima of 520 nanometer wavelength coincide. This result shows us how different wavelengths can align at specific points on the screen. Okay, so let's start by finding the least distance from the central maximum where the bright fringes coincide. Okay, so what is the least distance? It is the position of 4th bright fringe due to the wavelength 650 nanometer. So we use the formula xn equal to n lambda 1 capital D upon small d, and putting n equal to 4 here. So substituting the values into the formula, we have x4 equal to 4 multiplied by 650 multiplied by capital D upon small d. This calculation helps us find the position of the 4th bright fringe for the 650 nanometer wavelength. So the result for our calculation is x4 equals to 2600 multiplied by capital D upon small d nanometer. This tells us the exact position of the 4th bright fringe for the 650 nanometer wavelength. So finally we conclude that the least distance from the central maximum where the bright fringes due to both wavelengths coincide is 2600 multiplied by capital D upon small d nanometer. This shows us how different wavelengths can align at specific points, creating coinciding bright fringes. So this is all about today's lecture. I hope you enjoyed the session and understood it well. Thank you.